How's it going again, ladies and gentlemen? Mr. Johnny here, taking a look at 16.8 stuff, which is going to be about relationships between Ka and Kb. So our objectives will be to convert between Ka and Kb for an acid and its conjugate base or a base and its conjugate acid. All right. So, big idea, Ka and Kb are related by Kw. So Ka, let's take a look at this specific acid. I had hydrofluoric acid and it dissociated because it's an acid. What I'm going to get as my Ka is going to be shown over here. It's going to be a concentration of H plus times F minus all over HF. Now, if I take a look at the conjugate base, which would be the fluoride ion, and I looked at it acting as a base, it's going to have an equation that looks like this. Fluoride ions reacting with H2O, giving me HF and OH minus. All right, so the Kb for that is going to look like this. It's going to be the concentration of OH minus times HF all over the fluoride ion concentration. So, Ka and Kb are related by Kw. So let's take a look. If I got an acid, here's a generic equation for an acid. We got the acid breaking down into H plus and the conjugate base. And the Ka for that is going to be shown over here, which we've talked about a bunch already. So now let's take a look at the base. The conjugate base is going to be A minus, reacts with water, giving me the HA and OH minus. So the Kb is going to be what it is right there. So now let's see what happens when we combine them. All right, if I were to add these together, is there anything that cancel out? Well, let's take a look. I have A minus here and A minus here, so that cancels out because they're on opposite sides. I have HA here and HA there, and they cancel out. And what I'm left with when I combine them is H2O breaking up into H plus and OH minus, which is my Kw, right? Crazy. So now if I think about this mathematically with the Kas and the Kbs, what I'm going to do is, well, here's the Ka, and here is the Kb. And what happens when I multiply them is the same thing that we did up there. HAs are going to cancel out, the A minuses are going to cancel out, and I'm left with the Kw. So I know that if I multiply Ka by Kb, I get Kw. And I think I have it nice and big right here. So this is how the two are related. Ka and Kb are related by Kw. So what happens to Ka and Kb for the combined reactions? Well, conclusion was this. Ka times Kb equals Kw. Examples. Determine the Kb of a fluoride ion given the Ka for hydrofluoric acid is 6.8 times 10 to the minus 4. Well, I know that Ka times Kb has to equal Kw, and I know Kw is 10 to the minus 14. So if I want to get Kb, which is what I'm trying to solve for here, I can do a little algebra. Kb equals Kw over Ka. So now I just plug in the numbers. 10 to the minus 14 over that 6.8 times 10 to the minus 4 that they gave me right up here. And then I plug that into my handy dandy calculator, and I get 1.47 times 10 to the minus 11. And that is going to be my Ka. Not so bad. All right, so there's this other relationship where pKa plus pKb has to equal pKw, which equals 14. It's another way to do it. And remember that the p just means that it's negative log of whatever is in there. So pKa has to equal negative log of Ka. So don't let that confuse you. The p just means negative log of whatever came afterwards. This will be more important later when we get to like the Henderson-Hasselbalch equation, but we could do it this way too, right? We would get the same answer to the problem, but I don't like doing it that way. All right, cool. To summarize, Ka times Kb has to equal Kw. All right, when you combine the Ka for a weak acid and the Kb for its conjugate base, things cancel out and leave you with Kw. That's how we got that equation. All right, so I hope you found that helpful. I'll see you in class. Bring questions. Okay, bye.